The mathematical model for the wind turbine blade structural analysis is based on shell theory. The details of shell theory are quite involved, and the mathematics is quite detailed. However, one can understand it conceptually in a straightforward fashion as an extension of Euler-Bernoulli beam theory. And if you're not familiar with the Euler-Bernoulli beam theory, I would suggest that at some point you go through the cantilever beam module where I apply the Euler-Bernoulli beam theory in answers to analyze a cantilever beam. And in terms of the wind turbine blade, the mathematical details are very complex in applying the shell theory to that particular example. However, we have a fancy calculator at our disposal that will take care of the mathematical details, and so we can focus on the physical principles on which that mathematical model is based and the assumptions embedded in that mathematical model. First, let's talk about Euler-Bernoulli beam theory. If you looked at a simple cantilever beam like that, that you had a load over here and you fix it, say at this end, okay, and to figure out how the beam is going to deform, you focus on the midline, which I've sketched in over here, and you say that, hey, the midline under the influence of this load, which I've shown schematically over here, is going to deform something like that, and I've exaggerated the deformation. So if I have a point on the midline like that, it's going to move, in the y direction, that's in the transverse direction, to over here. And I also assume that, any cross section like this is going to rotate together on the whole. So if I show the cross section like that, it's just going to rotate, as a whole, and that should be 90 degrees, and it doesn't look like that. That's an assumption built into Euler-Bernoulli beam theory. You say plane sections remain plane usually. That's how you couch it, and then you say for small deformations that the rotation angle of the cross section is just given by the slope of this curve. And that means that once I know if I have a point like that on the cross section, it'll go over here, and if I know the deformation of the midline as well as the slope, then I know where I can back calculate where that point moves. So it reduces to figuring out what is the deformed state of the midline. And as we saw in the cantilever beam example, once we know that, we can figure out what the potential energy of the beam is going to be, because we know how every point is going to move, the displacement at every point, from which we can calculate the strains, and from the strains we can calculate the stresses based on the material properties, and from that the potential energy. So we need to find the deformed midline such that the potential energy is minimized. Plate theory, which is a simpler form of shell theory, takes that same, you would look at, say, the same beam, and instead of focusing on the midline, what you do is you focus on how the mid surface is going to deform. Okay, so here is the mid surface. Pardon my chicken scratch, but I think you get the idea. And under the influence of a load like that, we assume we have the same load here, it's fixed over here. I'm not sketching it in the interest of simplicity. And under the influence of a load like that, it's going to deform like that. So if I take a point over here, okay, it's going to move. Actually, it should, under the influence of a transverse load, it's going to move only in the transverse direction. So it's going to move over here. And And then you say, you know what, the normals are just going to stay normal. So if I had a normal like that over here, that's going to still remain a normal, okay? So instead of looking at the, saying that the cross section rotates together as a whole, you would say, the normals rotate together. So which means that if I have a point over here like that, pardon me, it's going to move over here, okay? Which means that analogous to here, if I know how each point on the mid surface moves, okay, so if usually you would say this is the x direction, let's say that's the y direction, and the normal is denoted as z direction, in plate theory and shell theory, as opposed to y over here. Slightly different notation. So you need to know, this is a key displacement. You want to know how each point on the mid surface moves normal to itself, and the point on the mid surface can also move in the x and y direction. And you want to know how the normals at the mid surface rotate. So you need to know theta. So here, the rotation is about y. You could also have a rotation about x. Think about it. And then you could also, generalize it to have like an in-plane rotation. Okay, you could generalize this idea to have all three rotations of the normal. That means if I know the displacement and the rotations at the mid surface, I can back calculate how every point on the within the beam moves. So if I know the deformed mid surface, I can figure out what the potential energy of the structure is. I would need to know the thickness. I think that's obvious, because the whole this normal is as high as the thickness, or half the thickness in one direction. And so I need to know the thickness, and then I can find the strains, and from the strains I can find the stresses if I know the material properties. And then the problem reduces to finding the deformed mid-surface such that potential energy is minimized. And what shell theory does is it takes this idea and it generalizes it to curved surfaces. Let's take a look at that next.